Hello, in Trig, Q4 week 7. This should be our last video of 2020. So this week we are learning about hyperbolas. So we've gone through conic sections, talked about parabolas, talked about ellipses, and now we're talking about hyperbolas. We're not going to do a lot of talking about circles because circles is covered in geometry. So what exactly is a hyperbola? So a hyperbola is one of the conic sections. So if we remember, we take a line and we spin it around and create these two cones that are end to end. And then we take a plane and we slice through the cones in different orientations and we can generate each of the conic sections. So if you take a look at this diagram, circles are the ones that we start talking about in geometry. Circles are the basic one that we have. And you see the plane is perfectly flat right here. An ellipse is when the plane tips over sideways a little bit and then our circle gets stretched out. A parabola is up here at the top of the cone, cutting through like this, and then it only cuts through one cone, can't touch the other one. Hyperbola is when you have the plane at such an angle that it has to go through both the cones. It doesn't have to be straight up and down like this. It could be tipped over a little bit to one side or the other. But a hyperbola is generated from cutting through the two cones with a sort of vertical plane like this. So now we know how it's created. What's the definition? How do we know a hyperbola is a hyperbola? Well, our trigonometric definition for a hyperbola. It is considered to be the set of all points in a plane whose distances from two fixed points in a plane in the plane, same plane, have a constant difference So we saw with a parabola, it was always the same distance from the focus and the directrix. So this one, we've got 2 points, and the hyperbola has a constant difference in the distance from those points. So it's not a constant distance, it's a constant difference, which is interesting and weird, but let's see what that means. So these fixed points are the foci of the hyperbola. The line through the foci is the focal axis. The point on the focal axis midway between foci is the center. The points where the hyperbola intersects its focal axis are the vertices of the hyperbola. So these are our key points, key parts of a hyperbola, key characteristics. So we should be able to identify each of these. And if you notice, they are very similar to the ones that we've talked about for every other conic section. So let's see if we can draw a diagram with each of these things on here. Okay, here we have a diagram of a hyperbola. So hyperbolas also have something called an asymptote. So if you remember from maybe algebra 2, an asymptote is a line that the function will never touch. And yes, the hyperbola doesn't actually fit our function rules, but that's okay. We're going to look at this red line, this curve right here, and we see that this curve goes along here, will never touch this asymptote line, and it won't touch this one either. So we've got our vertex right here. We can see that's the point where the hyperbola touches its focal axis. So there has to be another vertex over here, so that's this point. We have the foci, here's one focus, and here's the other focus. We can also measure A and C. So the distance from the center to the focus is our C. That's the same as it was for an ellipse. The distance from the center to the vertex is the A. And where it differs from an ellipse is A usually was bigger than C because an ellipse goes outside its foci. Well, hyperbolas go inside their foci. So A is going to be smaller than C because the hyperbola needs to be inside this focus point. This side of the hyperbola is inside the focus point. It's in between the focus and the center. On the ellipse was outside everything. The center and the focus were inside the ellipse. So when we measure eccentricity, we can do that for a hyperbola also, but you'll notice it's a little bit different of a result when we do hyperbola's eccentricity versus when we do an ellipse's eccentricity. So we said in our definition that the difference of the distances from the foci to each point in the hyperbola is constant. So what would that look like? So if I have a point on the hyperbola, let's take a random point right here. So what I'm saying when I say the difference of the distances from any point to each of the foci, I'm going to measure from this point to this focus, and let's call that distance 1. Then I'm going to measure from this point to the other focus, call that distance 2. The difference between these points will be the same for any point I could pick on the hyperbola. I could pick a point over here, and I could do the same thing, measure the distance from here to the focus, D3, measure the distance from that point to the other focus, D4, find the difference, and the difference is going to be the same no matter where the point is. And I could flip over to the other piece of the hyperbola pick a point, find the difference. The difference between the distances to the two foci is the same no matter where you are on the hyperbola. Okay, there's another couple things we want to talk about on this diagram. So we have an axis. There's a semi-major, semi-minor from the ellipse. Well, there's an axis called the transverse axis. So this means it basically that it crosses. It goes across from one side to the other. So the transverse axis is the axis that is lying on the focal axis and connecting the vertices. So if I draw from here to here, that is my transverse axis. Its length is always, probably figured out looking at the diagram, 2a. There is another important axis that we will talk about sometimes, and that is called the conjugate axis. So the conjugate axis is a weird one. Its length is 2b. And it's perpendicular to the focal axis. And has the center as its midpoint. So what that means, if we put this on the diagram, is there is some axis that goes right here, and the length of one side here is b, and the other side here is b, and this is called the conjugate axis. So we had the semi-major and semi-minor, major axis and minor axis and ellipse, and their measurements were a, b. We have the transverse axis and conjugate axis in the hyperbola, and they lie in the same area because they're all related. So instead of semi-major axis like it says on this diagram, you might also hear semi-transverse axis. And that is always a. You might also hear semi-conjugate axis. And the length of that is always b. Okay, we're going to put all this together into the standard form of a hyperbola. Standard form of a hyperbola. So the standard form for a hyperbola centered at the origin is y squared over a squared minus x squared over b squared equals 1. And we saw in the diagram previously where a and b kind of come from. So this tells us our semi-transverse axis and our semi-conjugate axis. We can also find out what our asymptotes are by replacing this 1 right here with a 0 and then solving and sorting it out. And so then once we solve, I'm not going to do all that work for you. You can do that on your own if you want. But once we put that a 0 in there, and if I solve for y, I'll get the formula for my asymptotes are y equals plus and minus b over a x. So this is a linear equation, and it's got a y-intercept of 0, so there's no term being added to this x term. So these are just linear equations for our asymptotes. And this is only for center at 0, 0. If we shift our center to HK, then it changes what this is. So let's make a little table writing down all the formulas we need that will help us to find all the key points of a hyperbola. So we'll start with hyperbolas with center 0. 0, 0. So we're going to have hyperbolas going two different directions. We can have a hyperbola that opens sideways, right? Or I can flip it around and I can have a hyperbola that opens up and down. So we're just flipping the focal axis. So in this first one, the focal axis runs this direction. And the second one, the focal axis runs that direction, vertically. So we call this one in red a horizontal. We call the one in green vertical. Even though, kind of you could argue either way, this is just the standard way we name them. So, standard equation for a horizontal one with a focal axis and the x-axis. Standard equation starts with x squared over a squared minus y squared over b squared equals 1. And then we just flip that for our vertical one. So the formula is y squared over a squared minus x squared over b squared equals 1. So the focal axis, this one is the x-axis. And the focal axis for this one is the y-axis. The foci for each of these. The foci on this one has coordinates of plus and minus c0. And our vertical one has the foci coordinates of 0, plus and minus c. Then we have the vertices. So the coordinates for our vertices are plus and minus a, 0, 0, plus and minus a. So starting to see kind of a similar pattern to what we've seen so far with the ellipses and hyperbolas. We've got C and A, and then we need B to come in somewhere, and we have the Pythagorean relation that we can use for each of these to find out B if we have C and A, or find C if we have A and B, etc. So Pythagorean relation, remember, is c squared equals a squared plus b squared. So we just rearrange it depending on which one we're working with. This one's usually the formula we use for Pythagorean theorem. A squared plus b squared equals c squared. So make sure you keep your Pythagorean relation connected to the specific conic section that we're talking about. So semi-transverse axis is the same for both of these. Doesn't matter which one it is, their lengths are both a. The semi-conjugate axis is b. And if you notice, most of these are basically the same. It's just my x and y switch, which makes sense if I'm flipping it over the xy axis. One's got the x-axis, the other's got the y. I gotta flip my x and y's. So a lot of these are the same. Let's see, the formula for finding the asymptotes is different for each of these. For our x-axis, focal axis, we have y equals plus and minus b over a x. Because we have two asymptotes, so it's got to be plus and minus. And then for our y-axis, focal axis, or vertical one, we have y equals plus and minus a over b x. So your a and b switch places depending on which direction it's pointing. So those are our major key points for a hyperbola with center 0, 0. If we have center hk, that's going to change. At this point, if you've been paying attention to the patterns that we've seen so far for parabolas and ellipses, when we go from 0, 0 to hk, you should probably be able to figure out what is going to change in each of these. So let's write down all the key points and features of a hyperbola with the center at hk. So again, we've got the two different ways that hyperbolas can be drawn. One that goes this way, and the other one that goes this way. So, standard equation. For our kind of horizontal one, we have x minus h squared over a squared minus y minus k squared. Whoops, wrong place. Squared on the outside over b squared equals 1. And for our vertical one, we're switching our x's and y's. So we have y minus k squared over a squared minus x minus h squared over b squared equals 1. Okay, the focal axis, where does it lie? It lies in the same direction as the x and y axis, but now that we're not centered at 0, 0, it's not the axis. It's close, but something different. So focal axis is going to be y equals k, and focal axis for this one is going to be x equals h. So we got a horizontal focal axis and a vertical focal axis. Coordinates for our foci. So foci's coordinates are going to be h plus and minus c comma k, and for this one is going to be h comma k plus and minus c. Our vertices. So coordinates for the vertices, h plus and minus a comma k, and h comma k plus and minus a. Semi-transverse axis. For both of these is a. Semi-conjugate axis. For both of these is b. Pythagorean relation. It's going to be the same for both of these. C squared equals a squared plus b squared. And then we have our asymptotes. So these are straight lines. So our formulas are linear equations, so y equals plus n minus b over a times x minus h plus k. So that's for our horizontal transverse axis. And then the equation for the asymptotes for the other one is y equals plus n minus a over b x minus h plus k. Okay, it's about time to do an example. So we're going to find the equation of a hyperbola. So find the standard form of the equation for the hyperbola whose transverse axis has endpoints -2, -1, and 8, -1, and whose conjugate axis has length 8. Okay, so the first thing I want to do is I want to sketch some of this information on here so that I kind of get an idea of what's going on with this hyperbola. So I'm going to give myself some space and go ahead and put this information on just a sketch of the graph. So I'm just going to draw real quick XY axis. And it tells me in the problem that I have the endpoints of the transverse axis. Transverse axis has endpoints -2, -1, and 8, -1. So I'm going to plot those points. I'm going to say my scale on this graph is, I think we can do it in ones. So I'm going to put my points -2, -1, and 8, -1. Oops. Didn't go down one. 8, -1. So that is my transverse axis. Then it tells me the conjugate axis has a length of 8. So it's going to be centered in between these points, and it's going to be perpendicular to the transverse axis. So the transverse axis goes this way. The conjugate axis has a length of 8. So halfway in between these points. Let's see how far it is. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So halfway in between is 5. That's going to be the halfway point. And then this conjugate axis has a length of 8. So I'm going to go 4 in each direction. Oh, need a little more space. So this has a length of 8. From here to here has a length of 8. So if we think about where a hyperbola lies, we can see which direction this is going to face. So graphing it out like this and plotting the information that we're given helps a lot. I can automatically see that this point right here is my center. And it's pretty easy to tell that the center has the coordinates 3, -1. So usually we use HK, so we know that H is 3, K is -1, because that corresponds with the center. So the standard form for this type of parabola, the standard form of its equation, looks like x minus h squared over a squared minus y minus k squared over b squared equals 1. I can use the distance formula to figure out my a and b, or I can also just kind of count it on here. To find a, it's going to be 8 minus -2 divided by 2. And if we count that up, we saw that was 5. B is going to be half of 8, because we're told that the full axis is 8, so the semi-conjugate axis has a length of 4. So we've got our h, k, a, and b, and we can start plugging things into this formula. X minus h, which is 3 squared, divided by 5 squared, minus y minus k, so minus -1, squared, divided by 4 squared equals 1. So let's simplify what we can and get the correct form of this equation. So x minus 3, don't have to do anything with that. That's just x minus 3 squared over, going to do 5 squared and get 25, minus y minus -1, minus negative turns into a plus or positive, y plus 1 squared divided by 16 equals 1. And this is the final form of that equation. That is the standard form. So I will see y'all on Zoom on Wednesday. If you have questions, send me an email. And what we're going to do this week is a little bit different, so look for a post in Google Classroom giving you some more information on what's happening this week.